yet, so all of these might be. I'm not expecting everyone to get like 12 out of 12 or anything, but there's one up here that I think is extra special twist of the knife. It's 4.
Yeah.
Right.
That's so fun. No,
You need to go ask Mr. Packer questions.
I would just do that. Just walk in.
Oh, he's not.
That'd be terrible. No, that'd be terrible.
Not here.
And they told me that each of the
Yeah.
chickens weigh 10 pounds each.
He wasn't here yesterday.
And I
Yeah,
said, no,
I
no.
don't know.
Yes.
The son was like, he's not here today.
I mean, it's
Maybe
such a big
we
egg.
were like, oh, nothing. She's like, I don't know.
We already finished
It's
the
one,
game.
two,
It's
three,
okay.
Then you see the take like a better like a brain snap.
Am I good to go through, or you guys have one more time? One more time. Wait, you said that? You said a little more time. And I was like,
Yeah, I was like,
5
yeah.
seconds.
Yeah, one more time. Just need to get 12 done.
Okay, let me talk through these. Please stop me if you have a question. So if you see percent of variation of the data, you should not be thinking R. That is false the way it's written. What should you be thinking? You should be thinking R squared. So when you see this phrase, that tells you R squared. Residual is not predicted minus actual. It is actual minus predicted. So you find the y value that you have, you subtract the predicted y value, remember the hat means predicted, and that's your residual. Outliers in the y direction are influential points, so we talked about, like, if I have some data here, a point up there is not really going to do much. It would probably bump my line, like something like that. That was really good. But an outlier in the x direction, like over here, would do something. So it's not outliers in the y that are influential, it is outliers in the x. So 3 is also false. Question on the first 3? If I remove a point with a large residual, the relationship gets stronger. So if I have something like that, this point has a large residual because it's the furthest away from the line. So if I take that point away, well, let's start here. Is that a point that is weakening the relationship or strengthening it? That point is weakening it because it's far away. So if I remove it, it's therefore going to strengthen it, right? If I remove a weak point, so that one is true. 4 is true. Number 5, if the slope of the line increases, the y-intercept decreases. So if the slope goes up, doesn't that make the y-intercept have to come down? If the slope goes down, the y-intercept goes up. So these always work in opposites, so that is true. X is the explanatory variable, that is also true. Question on the first 6 there? 7 is the one that I'm guessing might have tripped some people up. So even if you knew this, percent of variation explains, that's R squared. You're feeling really good about yourself because you're like, yeah, I recognize that. That's R squared. Okay, now I got to get to R. So how do I go from R squared to R? You square root it, and then a bunch of people will tell me it's 0.8 for sure, and they'll stop and say that's true. So the tricky thing is here, there are actually 2 square roots of any number, right? Like square root of 9 is like 3 and negative 3. So the square roots here are positive or negative 0.8. And I don't know which one unless they give me more information. So I would need to know, like, whether the graph is positive or negative, whether the slope is positive or negative. I don't know that in this case, so to say it must be positive 0.8. Well, if you got to 0.8, I'm like pretty happy because you knew most of the problem. It doesn't have to be positive 0.8, it could be negative. Sounds a little trickier. Does that make sense for 7? And then 8, there's nothing you can do to change R. So if I switch the variables, R would change? No. If I add a billion to everything, no, it doesn't matter. If I eat more food, I'm going to gain more weight. It doesn't matter how you measure the food or my weight. It's just a relationship that's there. It's going to happen. No matter how you measure it, graph it, whatever. 9, I could see, like, you also I think Kyle wants you to talk about outliers too when you describe the graph. So this is a little iffy. But you should describe all these things. So I'm going to say this is true. You can discuss outliers also if you want, but I should discuss form, which one of my options there? Linear, non-linear, direction, positive or negative, and then this is like your strong, moderate, weak type thing. And then don't forget context, that's like labeling your graph, right? If the residual plot shows no pattern, so if you get something like that, does that mean the original data is linear? It does. Because that was really just the line, like flipped sideways. If your residual plot looks like this, what does that mean about your original data? It's curved. We don't know if it's exponential or power or whatever. It's curved. So if you see this on a residual, your original data is not linear. If you see this, it is linear. Number 10, that is true because the cost responds to the number of toppings. So the cost is going to change based on how many toppings. And then number 12, I don't think we've talked about yet. Extrapolate. So extrapolate is like if I have a bunch of data here between like 50 and 60, and I get this pattern, so I got this. Is it okay to use this data set to predict what happens when X is like 55? Yeah, that's totally fine. That's called interpolate because you're going like within your data set. It would not be okay to use this line to predict what happens when X is 100 because I don't know what happens out there. I can't just assume that this pattern continues. It could be once I get past 60, it drops off, it could go up there, it could stay flat, it could get bigger and bigger. But you can't like assume the pattern continues. Extrapolating is assuming your pattern continues. And we don't want to do that, so that is false. Questions on this little warm-up guy here at all? Okay, let me go through computer outputs with you. This is the one section on Khan we didn't quite get to. And I'm just going to pull mine up. I know it's different problems than yours, but I'll get the point across. So we need to know like what this table means, what they're trying to give us here. So I look at this problem. We're trying to predict the height of an adult man based on their father's height. So right there, I can start writing a couple things down or noting a couple things. If I'm trying to predict the height of an adult man, that's what I'm trying to predict. So that's my Y. Based on their father's height, so that's my X. Took a large sample, blah, blah, blah. Here's the computer printout. Okay. You will never use that column. You will never use this column. We will use this column, but not until like May. So none of this stuff matters. S doesn't matter. And in this specific problem, R squared doesn't matter. So really, this is what you're dealing with. It's just these, and this is what you're going to see it every time. You'll see like a constant and a number next to it. And then this right here is always your X variable. So father's height is always the X. Or whatever you see down here is always the X. That number next to the X, when we're doing like Y equals MX plus B, what does the number next to the X tell us? What does the number in front of the X tell us? It tells us slope. Same thing. So the number next to the X is our slope. Don't be jealous of my handwriting. Oh, you can see it. I worked so hard on that too. Slope. And then this number up here, it's got constant next to it, so that's not a variable. That doesn't change. That's like your starting amount, and that's your y-intercept. Sometimes it'll actually say intercept right here instead of the word constant. So if I were to write out this equation, it would be y hat equals 0.431x plus 100. This is painful, I'm sorry. 0.6. You know what I mean, I think, right?
Yeah.
Okay. So that's my equation, but they're asking me a little bit more than that. Use this model to predict the height of a man whose father is 175 centimeters tall. So father's height is x. So you would take 175 and do what with it? Plug it in for x and then figure out what that is right there. Ignoring my super awesome handwriting. What can I go over there? Like, where'd you get this from? Why is this here? Is that alright? Let's say 4, 2. Oh, darn it. Can't believe I didn't get it. Alright, similar idea here. So all that matters, let's just box around what does matter. All that matters is that. So what is your x variable in this scenario? Mileage. So you could probably do this without reading the question if you just look at the answers, but you can read the question or the answers for this one. What's the y variable? Y variable. Price. So I'm asking for like this part, this piece right here. And then this number, the 0.246, goes with the x or the y? Goes with the x, so it goes with mileage, right? So you want 0.246 times mileage, or negative 0.246 times mileage, so it's going to be either B or C. And then this number is your y-intercept. So that goes there. That goes there. And then mileage or x goes there, so it should be C. Does that make sense where I'm getting that from? Do you understand why I'm picking C? Try that one. I won't say anything. So views is your x. That's the slope, so it goes next to the x. So it should say 0.034x, or 0.034 views. And there's only one that does that, isn't there? So I know it's this one right away, but let's just double check. So the constant of the y-intercept is 0.42. So that's the number that goes by itself. There's your slope, and then views is your x. That should be B. I'm going to add B in your brain. Okay. That's all I got for you. Like, we're technically done with the chapter. Like,